Monday, February 5th, 2024, relativistic Rivas. In red, the electron mass trajectory. In blue, the zitter fast dynamic, also relativistic. Here I display stable orbits. I clearly see S1 type electron orbits around a gold atom and what looks like almost S2 type trajectories around the gold atom. Here's the replay of an S1, and the electron radius in red is going to stabilize eventually. It looks like a periodic orbit of some chaotic dynamics. Also non-conservative. Electron coming in at 1.2 10 to the power 5 electron volt, and coming out between 1, 3, and 2 up to 3 10 to the power 5 electron volt. You can see here. In red, the electron mass. In blue, the zitter. The orbit is now a nice circle. It seems to drift, and it is not centered on the electron, in the proton, gold proton center, but it is rather a stable circular orbit. Spin 1. There's also Mott asymmetry in here, where everybody's okay, meaning there's no blowing up. The relativistic simulation finishes. We have 30,000 positive, 3,000 that backscatter, so we observe Rutherford scattering, Mott scattering at 120 left, 60 instances, versus 120 degree right, 37 instances, spin asymmetry that we observe here. This is done replaying. We're going to replay one of the S2 orbits. Here the spin direction of the electron mass is reverse. Again, the orbit is a little bit all over the place in terms of radius. It's It's actually not circular. I call it S2, but I think that's just an abuse of language. They look rather the orbit is a parabola. Just looks circular on average. Everybody, however, is well behaved in terms of the integration. It does not blow up, it finishes nicely. Let's look at another one of the big orbits. Same thing, reverse here, meaning left spin and inside cusp of the zitter. This is a 1.35 10 to the power 5 electron volt from a 1.20 K electron volt start, so it's non-conservative. But the gamma is well behaved. We never blow up here. So I think this just indicates a non-conservative dynamic due to the forcing of the deBroglie clock here, the blue zitter, Zitterbewegung, the jittery motion in blue. This is 1,000,000 steps. I do not know that this is a periodic orbit long term. It does seem to drift. And I think we're done. Let's go look at a small orbit. Here we observe a right spin of the center of mass and the zitter cusp outside. And we observe the stabilization of the orbit. There's no discontinuity in terms of, there's always a clean distance. This is 10 to the power minus 13. It's the Compton distance. And it's just captured due to the non-conservativeness, or what I observe to be a non-conservativeness. Here the energy coming in is 1.2, 120 kilo electron volt, coming out 176 kilo electron volt. And again, stabilization of the radius, drifting. Even though it's drifting, this one seems rather stable. Again, this is 1 million steps. And for the fun of it, we will do one of the big ones. That looks rather chaotic here. Let's go. Again, the inverse. A left spin with the cusps inside. And here, it looks like we never stabilize as well as we do the others. They all have the same spin. This one is definitely wobbling about. It seems stable as it does so, in the sense that this radius, which gets overwritten here a lot by the zitter orbit, seems rather stable. But the orbits are parabolas. Maybe one more of the small ones. This should be a right with cusp outside. Notice the small radius at first. That seems to increase and stabilize over time. This is actually deeply non-relativistic here. I can't tell with the fast ones, but the energy out is 188 kilo electron volt. So again, non-conservative from 120 kilo electron volt. All the readings are simulation okay, meaning gamma remains well behaved. Here max gamma is 5. So it never explodes. Interestingly, if the zitter is non-present, if the zitter radius is 0 as opposed to 1.93 10 to the minus 13 meters, if the radius is 0, no zitter, then gamma explodes. The simulation is not stable. The forces are too strong, and simulation runs into trouble in this region of 10 to the minus 14, 10 to the minus 13 meters, 10 to the minus 12, which is the Compton radius. All right. And that's good enough.